Welcome to section 6.1. We're doing discrete random variables. So we're going to start building our distributions now that we have all the probability from chapter 5 understood. And one of the things that we're going to begin to do is define what a random variable is. And essentially we're going to be able to take a qualitative variable and turn it into a quantitative variable. All right, so we're going to start by an experiment. Let's start by flipping a coin. And we'll start by flipping a coin. I'm going to write twice, and that's our little experiment. And what kind of things can we get from flipping a coin twice? Let's define our sample space. Well, we could get 2 heads. We could get 2 tails. We can get 1 head, then 1 tail, or 1 tail and then a head. So there's 4 outcomes in our sample space. And again, how I have this written, these are qualitative variables. And with qualitative variables, we can't do much as far as calculation goes, because we can't do addition, subtraction, multiplication, division with words. So what we could do is we could come back if we wanted to run some sort of calculation on this, and we could define a capital X to be number of tails. So we would count the number of tails rather than listing it out as an outcome. All right, so in this case, if we go through our outcomes, this one had 0 tails, this one had 2, that one had 1 tail, that one had 1 tail. So our options, our sample space for this capital X would be 0, 1, and 2. All right, and so when we do this, now we've turned this qualitative variable into a quantitative variable. And this X is actually called a random variable. And that's the title of this section. And the values of X, the observations take on little x. And again, we can have 0, 1, or 2. All right, so big X is the number of tails, it's the random variable, and then little x is all the values. All right, so let's start formally defining everything. A random variable is a numerical measure of the outcome from a probability experiment. So its value is determined by chance. All right, so it's from a probability experiment, like flipping a coin. So the value of the random variable is determined by chance. And we use letters such as capital X. All right, our particular example, flipping a coin and counting the tails, was a discrete random variable because it had a countable or finite amount of values. Another way of thinking of this is we can plot the discrete random variable on a number line, and there would be space between each point, versus a continuous random variable that has infinitely many values. All right, we kind of already talked about this from chapter 1. And now when we go to plot those on a line, it's just a continuous line. So there's no spaces in between the numbers, the values. All right, so let's look at the examples. Let's determine whether the following random variables are discrete or continuous, and then we'll state some possible values. So first we have the number of light bulbs that burn out in a room of 10 light bulbs in the next year. So there's a room with 10 light bulbs in it, and the discrete variable, or excuse me, the random variable, I just gave away the answer. The random variable is the number of light bulbs that burn out. And because we can count those, like I just said, this is discrete. And the values of the random variable, we can write that 2 ways. We can say the little x, whoops, that's little x. Let's see, we could have 0 bulbs burn out, we could have 1 bulb, 2, 3, all the way up to all the bulbs burning out. So there's 11 values that our discrete random variable takes on. dot, 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 continue in this fashion, all the way up to 10. All right, the number of leaves on a randomly selected oak tree. Again, we could count the number of leaves, so this is going to be discrete. And some values, let's see, if it's winter on an oak tree, is that a deciduous or an evergreen? I think it's a deciduous tree. So there could be 0 if it was, let's say, dead, if it is an evergreen tree, or 0 if it's winter, 1 leaf if it's fall, 2 leaves, 3 leaves, 4 leaves, all the way up through spring. How many leaves do you think are on an oak tree? Probably more than 500, but I'll just write 500. All right, and then the length of time between calls to 911. Well, the length of time, that's a measurement. It's a measurement of time. So this would actually be continuous. And some values of the variable. Well, maybe it could be an interval of time. Maybe they call, or a toddler calls 911 and the mother hangs up before they even answer. So maybe it could be 0 seconds all the way up to maybe like, oh wait, the length of time between calls. Well, okay, we can still go with 0 minutes between calls, and then I'm assuming that people call 911 a lot. So maybe anywhere between 0 to 15 minutes. Okay, so the important thing to remember is the actual value of x is determined by chance. So all of these different values are going to have different probabilities, and I'm going to highlight that. So the different values will have different probabilities. And so we have to organize that information, and we're going to organize it with a table, graph, or formula. So in a table, it's called a probability distribution. It provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. Okay, so it follows 2 rules. So if you're ever asked to check if something's a probability distribution, you're going to check 2 things. You want to make sure all of your probabilities of the values of the random variable are between 0 and 1. That's like 0% and 100%. And if you add up all the probabilities, you should get 1, right? So the parts add up to the whole. All right, so notice we have a probability distribution. So we're going to be creating distributions. And whenever we have a distribution, we look at the 3 characteristics, and we've talked about these before. We talk about the shape. So bell shape, skewed right, skewed left, or uniform. We talk about the central tendency, so mean or median. We don't really use modes so much. And then we talk about the spread, which is like the standard deviation or the IQR. All right, so let's look at an example of a probability distribution in the shape of a table. Here's our example we're going to be using. So the table shows the probability distribution for the random variable x, where x represents the number of movies streamed on Netflix each month. So there you go. So x represents the number of movies streamed on Netflix each month. So it looks like the value of our random variable ranges from 0 movies to 5 movies. All right, so obviously this is a little outdated. I think people sometimes stream 5 movies a week these days. But this is what it is. Okay, so it's a probability distribution, so let's ask ourselves these questions. Are all the probabilities between 0 and 1? And we can just do a quick scan. Let's see, 0.6. This is the probability that someone will stream 0 movies, the probability they'll stream 1 movie, the probability 2 movies, etc., etc. And they're all between 0 and 1. No negative numbers, no 1.05s. So that's good. And now the next thing we look at is the sum of all the probabilities, does it add up to 1? Okay, so if we were to add up all the probabilities, would we get 1? So let's, and we do indeed get 1. All right, so this is a probability distribution. All right, so what we can do with this is something similar we did in chapter 2. Once we had our frequency distribution, we made a frequency histogram. Now that we have our probability distribution, we can make a probability histogram. And it's created the same way. The horizontal axis corresponds to the value of the random variable, and the vertical axis corresponds to the probability that that random variable will occur. All right, so we're going to draw a probability histogram of the streamed Netflix movies. All right, so again, just to clarify, number of movies streamed, that's the value of your random variable. I'm just writing this for clarity. This isn't something you would actually need on a histogram, but we're learning, so I'm writing in extra information. Okay, and then on the side, this is our probability of each one of these things occurring, probability of X. All right, and then going up to our table, it looks like the highest one is 0.58. So how many do we have here? 1, 2, 3, 4, 5, 6. So each little line will be a probability. And we can start with 0.1. Here's like 2%. I'm going to go by 2s because I'm running out of room. All right, so each tick mark is 0.1. All right, and so histogram, we know the bars touch, so I'm just going to make spaces for my bars first. So for discrete variables, not continuous variables, but for discrete variables, the number is normally right in the middle of the bar. And the probability that they stream 0 movies is 0.06. So a little over halfway on that first notch. 1 is 0.58, so almost all the way to the tippy top. Woo. 2 is 0.22. 3 is 0.1. All right, that's that. 4 is 0.03. And then 5 is 0.1. 0.01, excuse me, I did it again. Okay, so now we have our distribution. So once we have our distribution, we can also talk about the shape of our distribution. And what shape is this? Well, we have our extreme values to the right. We have our right tail. So this is skewed right. Something like that. All right, so we are eventually, in Chapter 7, we're going to be bridging the gap between this histogram and probabilities. Even more so, we just kind of touch on it in Chapter 6. So what I want to do is I want to focus on this square. Oops, right here. And I'm going to just bring it down. And we're going to talk about the area. All right, so from above, the area of a rectangle is, drum roll. Okay, so let's talk about some measurements of our square because we're focused on the area of our rectangles. What is that width? Well, these discrete variables up here, they're kind of like a midpoint. So we're going 0 to 1 to 2 to 3 to 4. This width is 1. The height is the probability, and so we've already established that to be 0.22 from the distribution table. And so our area of this rectangle is 0.22. All right, so the area is the same as the probability of that random variable, the value of that random variable occurring. So let's write that out. So from above, the area of the rectangle is, so I'll say area is the probability the random variable has that value. All right, and when it's discrete like this, that's kind of straightforward because each of these, the lengths of all of our rectangles will be 1 and the height will be the probability. So it's natural that the area is the probability, but when we start working with continuous random variables and our bars are no longer going to be 1, we'll be able to use this result still. All right, but we'll see more of that in chapter 7. Let's continue on with the mean of a probability distribution. It's really similar to a weighted mean. Actually, it's the exact same concept of a weighted mean. So I'm going to use mu of capital X, mu of X, is equal to the sum of the value of the variable, the value of the random variable, times its corresponding probability. All right, so this is like the weighted mean. This is how we calculated the mean from group data. All right, so let's do that example by hand. So we're going back to our stream Netflix movies. We're going to compute the mean of the probability distribution. So again, we're going to look at all these products, x times the corresponding probability, and then we're going to add them all up to get the mean. All right, so here we go. So this is going to be 0. 1 times 0.58 is 0.58. 2 times 0.22 is 0.44. 3 times 0.1, 0.3. 4 times 0.03 is 0.12. And then finally, we have this, and we add it up all together, and we get our mean. We get a 1.49. All right, and then it's a mean, so we need units. So what are the units in this case? It's 1.49 streamed movies. All right, and we'll talk about the interpretation in just a second. I want to stick with the calculation for now. So again, this was your mu of x. Okay, so this is only, there's only 6 possible values. So this was fairly easy to calculate by hand. But if it was larger, this would be kind of tedious to calculate by hand. So how we do it instead is we calculate it just like we were doing for the group data. So group data from chapter 3, section 3.3. So you put the value in a list, so put that in L1. The frequencies are now the corresponding probabilities. So put that into list 2. And then it's a 1var stats on your calculator. All right, so if you have your fancy screen, your data is L1, your frequency is L2. If you have the TI-83, you type this into your home screen with that comma. And then push enter, and you're going to get that big list of values, and you'll see that your X bar is 1.49. Okay, so let's see how we're going to interpret this. And we're going to interpret the mean using the law of large numbers, because remember, mu of x is from a probability distributions. And how we interpret probabilities is we use the law of large numbers. All right, so remember, we're getting this from a probability distribution. And so we're going to interpret it the same way we interpret probabilities. We're going to use the law of large numbers. Okay, so let's look at an example, or let's write that out. So really similar to what we were doing in chapter 5. Suppose we repeat a probability experiment, in this case, like flipping a coin twice. And again, law of large numbers, so we're going to be repeating it many times. Say 100. All right, and then every time we repeat this experiment, let's say it's flipping a coin twice, we write down how many tails we had. So maybe the first time we had 0 tails, then we had 2 tails, and then 1 tail, and then 1 tail, etc., etc. Whoops. And so if we have our experiment 100 times, we're going to have 100 values from our probability experiment. All right, if we were using our Netflix example, it would be like taking a sample or sampling from the Netflix customers and then writing down how many movies that person watched, then the second person how many movies they watched, and the third person how many movies they watched, all up to the 100th person how many movies they watched. Okay, so we're doing this a lot of times. In this case, I said 100. So if we calculate X bar from that sample, so we add up all of the observations, all of the values of our discrete random variable, and we divide them by the total amount of experiments, we would find that X bar will be pretty close to the theoretical value, which is mu sub x. All right, so let's apply it to our example. What is the interpretation of the mean in our example? Well, let's examine. So that's exactly what happened. So this data, this chunk of data right here, it represents the number of movies streamed on Netflix by 100 randomly selected customers in a single month. And we're going to complete the mean number of movies streamed from this list of 100. Okay, so that means we're going to add up all 100 of these discrete random variable values, and we're going to divide by 100. And in this case, we would actually get 1.49. So again, going back to the definition, we repeated the experiment a lot, like 100 times, and X bar, the sample mean, will approach mu sub x, the mean of the probability distribution, so the theoretical mean. All right, and then we get a nice little visual if we continue down our page. The horizontal axis is the amount of trials. So notice our horizontal axis, the trials would be sampling like 100 people. The vertical axis is the corresponding X bar. So for instance, when we sampled 100, we got something like 1.49 right there. And then this horizontal line that they have is mu sub x. So that horizontal line is your mu sub x. So when we didn't have a lot of trials, so it looked like maybe here we were sampling like 10 people, and these were the corresponding means we got from 10 people on the amount of movies they streamed. And then as our trial size increased, so as we got 50 people, we got a little bit closer to mu sub x. And then as we got larger and larger, like 100 people, we got really close to mu sub x. So all these little dots are the sample mean, and as they get larger, they get to our theoretical mean of the probability distribution. All right, so there you go. And again, this is one of the reasons why a larger sample is always better. It better represents the population, right? So here we might have had some extreme values when we don't have a large sample size, and they weren't balanced. But as you get a larger sample size, if you get some extreme values in your sample and it's a large sample, the chances that something that is there to balance it is higher. So everything balances out and represents what's actually going on. Okay, so mu sub x, because it happens when we have a lot of probability experiments, we can also think of it as what happens in the long run. So sometimes it's also called the expected value, and we use E sub x for the expected value. So let's look at an example using the expected value. So here we have that a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. I always like to highlight things that I think are going to be important. And then according to this report, the probability the female will survive the year is that, and we're going to compute the expected value of this policy to the insurance company. So how much money the insurance company is going to make. Okay, so expected value is your key word. So when you think expected value, we know expected value is mu sub x. We know that's a probability distribution. Okay, so a probability distribution has random variables and then the value or the corresponding probability. So we can start here. And we want to know the expected value of this policy to this life insurance company. Well, it depends what happens. So let's look at the qualitative variables first, and then we can turn them into quantitative. So the outcomes for this life insurance policy, they're going to make two different sums of money. One if the woman dies, and then one if the woman lives. So let's write that out here. So one if the woman lives, and then they'll make a different sum if the woman dies. All right, the expected value. Okay, so to the insurance company, if the woman lives, how can we turn that into a quantitative variable? Well, if the woman lives, we know that the woman gave $530 to the life insurance policy. So the insurance company will make $530. All right, and what's the probability of the woman surviving the year, the woman living? It's 0.99791. All right, let's look at the flip side. If the woman dies, well, first, the insurance company has $530 still, but they have to pay, so it's going to be a negative number for them, $250,000. So notice this is going to be a negative number right here. And it actually ends up being, let me write it out, negative, because that's important, they're losing money, negative 249,470. And the probability of that happening would be the opposite of the survival rate, the complement. All right, and then notice we're doing the complement and it's becoming our probability distribution, because now when we add up our probabilities, they will add up to 1. All right, so we created our probability distribution. Now that we have that, we could do the expected value, which is just the mean. So let's do our last column. You can actually put this in L1. You could put this in L2 and do a 1 var stats on L1, L2. Or to calculate the mean, we can quickly look at the value times the corresponding probability, because there's only 2 values. So 530 times 0.99791 is this. I'm going to go out 4 decimals. We don't like rounding till the very end. And then likewise, we're going to do, make sure you get the negative in here, times this very small probability. All right, and then to find mu sub x, we add up these 2 products. Now we can round to the nearest cent, because it's dollars. And we see that the expected value is $7.50. All right, so there you go, it's $7.50. So this also helps us with our interpretation of the mean, because if one woman were to find this life insurance policy, after a year, the insurance policy or the insurance company is not going to make $7.50, right? With one person, either that woman will live and they're going to make $530, or that woman will die and they'll be out that $249,470. So what does this $7.50 actually mean? Well, again, if we repeat the probability experiment a lot of times. In this case, it means maybe we have like 1,000 life insurance policies. So there's 1,000 women buying these life insurance policies. Some are going to live, a lot are going to live, most are going to live. And every once in a while, one of them will die. And so they're going to collect maybe $530, 999 times, and then maybe they'll have to do the payout once. Well, I guess they'll collect it 1,000 times, really, and then they'll have to do the payout once. And so overall, for all those thousands of women, on average, they're going to make $7.50 on each woman, right? And then times that by 1,000, and now you're looking at a nice profit, right? Okay, so let's write that out. So if there are a lot of policies, the law of large numbers, the insurance company can expect to make $7.50 per customer. All right, and this is the work of actuaries. One branch that you can go into if you major in statistics is to become an actuary, and they set these values for the insurance company, and it helps determine how much the insurance company is going to make. Okay, so we've talked about the shape of probability distributions. We talked about central tendency. Now it's our last, the standard deviation of a probability distribution. So let's give you guys that formula. So really similar to, again, the standard deviation formula for group data. So it's a standard deviation, so we'll be taking the square root. It's going to be the difference or the deviations from the mean. And we have to square it so it doesn't add up to 0. And then we're going to multiply it by its corresponding probability. It's like our weight. Then we're going to add all those up and take the square root. Okay, so let's do this one by hand. And then I'll do the first line with you. And then pause it, and I'll fill in the table while you guys fill in the table. We'll compare our answer. Remember, your mu sub x is 1.49. This is our Netflix stream movie example still. All right, so in this first example, we're looking at 0 minus 1.49, so negative 1.49. And we're going to square it, and then we're going to multiply it by and corresponding probability. Okay, and then whatever that is, we're going to add them all up here, and that's the sum. And then we're going to take the square root, and that will be our standard deviation. All right, there's a little magic for you. So we have our table filled out. You add up that last column and take the square root, and you get your standard deviation. And of course, we need units. So we would want to write the standard deviation is 0.9327 streamed movies. All right, and we did it by hand once, so from this point forth, we can use our calculator. And if we wanted to use our calculator, again, we can put, same setup as before, we would put L1 as our data, L2 as the corresponding probabilities. You would run a 1var stats. Your data would be L1. Your frequencies would be L2. So on the TI-83 screen, you would write 1var stats, L1, comma, L2, and then press enter. And you would get your sigma sub x, again, to be the 0.9327.